So our next lesson is going to be on areas in the plane. Now I can hear you already saying, all right, I got this area. Area, that's just an integral. And indeed, that is definitely one of the main applications of an integral. But you'll find out in this section that we begin to open up to more possibilities, more varied situations involving area. Plus, one of the main reasons we're looking at the area is so that in our next section, we can turn this into volume. So there's going to be a few things in this section that actually act as a good previews of our volume lesson. All right, so let's take a look at finding the area between two curves, which will actually end up being one of the main types of problems we do in this section. And so we have a pretty simple example here. An upper curve may be called f of x, a lower curve g of x. And we're trying to find that area, that yellow region between the two curves. Now, if we just do the integral of f of x, well, indeed, that would give us that area. That would give us the area to the x-axis. And if we just do the integral of g of x, well, that would give us the area under the x-axis. Of course, that area would be negative. So how would we make our how would we get a total area, as we called it a couple chapters ago, the total absolute area? Well, since, again, the green area would be positive and this blue area would be negative, all we'd have to do is subtract. And if we uncover our little rub-off here, sort of like the lottery, are we a winner? Do we just have to subtract? Well, yes. All you have to do is subtract the upper minus the lower. And this simple subtraction will become the main way that we process finding the area between two curves. Now, sometimes it's going to be helpful, actually I shouldn't say sometimes, it's really all the time it's going to be helpful to draw some rectangular strips. Drawing in these rectangular strips are going to help us to determine which graph is the upper graph, because of course that would be the graph that's touching on the upper side or the top side of my strip, and which graph's going to be the lower one. Of course, that's touching at the bottom of the strip. Now you might be saying, Mr. Naylor, really? Do I really need to draw a rectangular strip? Well, yes, because as we go a little deeper, we're going to learn that there's such a thing as a dx integration, actually the type of integration we normally do, but there's also going to be a dy integration. And a dy integration is going to be when we actually draw our strips horizontally, and you'll find out it's actually when the graphs are oriented differently. Instead of a top and a bottom, they'll be oriented left and right. So we're going to push this rectangular strip idea, and you'll be glad that you did it as we get deeper into these problems. Okay, now as always, push pause, take notes. A lot of these problems are intended for you to actually try on your own. And lastly, all these problems will involve graphing. I have to say that students that actually graph these problems on their calculator, like this first one, trying to think about the area between secant squared and sine, students that graph these on their calculator do better. So if we were in class, I'd be giving you time to do that, and I really encourage you to do that now during the video. In fact, right now, you should be pushing pause and just seeing what your calculator shows for this problem. Because the real question is, where is this area? Where is the area that's between secant squared and sine? Now, to graph secant squared, did you remember that that's 1 divided by cosine squared? Yes, you would type in 1 divided by cosine squared. Most likely in a Zoom trig format, you would have seen a graph that looked maybe like this. Now, you actually would have seen more of the graph. You would have seen graph that's maybe down here and down here, but what I'm doing is trying to help you guys to kind of focus in on the main part of the graph, that is the part that is going to be between 0 and pi over 4. Okay, and then you have the sine wave. Of course, you may have seen more of the sine wave, but again, we're really just looking for the part between 0 and pi over 4, which becomes our next order of business, of course, to locate those spots on the graph again, when you do your assignment, you're going to be getting visual again. You're going to be making a sketch for your problems so that you're able to see the area. Now, the area is definitely this region here, and so we can draw some strips. Now, when I draw a strip here, it's pretty obvious that the secant graph is the one on the top and the sine graph is the one on the bottom, so that I can get right down to business setting up my integral from 0 to pi over 4 of the upper graph secant squared minus the lower graph sine of x. And we have ourselves a nice little integral. Okay, of course you have to remember that you have to find the antiderivative of secant squared. Now the antiderivative of secant squared would be tangent. Okay, remember that's just like a basic rule. And of course the antiderivative of sine is actually opposite cosine, which would change our sign to a positive. Now I could call this capital F of x. We've definitely used that notation quite a bit. There's nothing wrong with doing that again. I can also use what we like to show you later in calculus is known as an evaluation bar. An evaluation bar is just a different way to say that I still need to do something with 0 and pi over 4. It's not an integral sign anymore. It's a straight vertical line. And of course the thing that I need to do is plug in pi over 4 and to plug in 0. Again, do this on your calculator. Actually plug in pi over 4. If you plug that into tangent and a cosine and add them together, you get 1707. If you plug in 0, you actually get 0 plus 1, which of course comes out just to be 1. Now I have to subtract these numbers. Make sure you understand that the number I just wrote down, 1707, that's the value of tangent and cosine. And make sure you understand that the number 1 that I wrote down, that's the value of tangent and cosine when I plug in 0. So I'm doing the subtraction, and I'm coming up with my final answer here. Okay, now that would be the area between, that would be that red region that we were seeking. Now, before we move on, I do just kind of want to highlight here that this was known as a dx integration. You might be saying, well, what's the big deal, Ms. Naylor? Isn't that always what we do? Well, it has been what we've done up to this point, but as we get a little deeper into this lesson, it won't be what we do all the time. But it was a dx integration because I drew vertical strips, because my problem was done in terms of x, and ultimately because my limits of integration were also given as x. All these things are going to come into play as we keep moving forward. Let's look at this one, the area between y equals x plus 1 and y equals x squared minus 5. And again, I say to you, this would be a great problem. You really do want to be graphing this on your calculator. In fact, every example we do has some kind of new nugget. And you want to discover the new nugget and maybe even try to figure out what to do about it. But I'm telling you, if you graph this, you'll get a little closer to that new learning. All right, so we've got ourselves a nice little straight line, x plus 1. You can use your calculator for that. And we got ourselves a parabola. And that parabola, x squared minus 5, might look a little like that. So what was the new nugget of learning for this problem? I don't think it's that hard to see that the diagonal line is the line at the top. If you draw a couple rectangular strips, you can see that that's the one that's on the top. But what about the area closed? What about the points of intersection? You see, the limits of integration were not given in this problem, so you had to determine them. But of course, they're easy to determine because they're just the points of intersection. Okay, but that is implied in this problem that we are going to be going from -2 to 3, and honestly, that's implied because it says we're looking for the area that's enclosed. Now, that's our little nugget of learning. If we do our rub-off of our lottery ticket here, we see that the intersection points, not much of a surprise, help us to determine our limits. Okay, so pretty easy. I can set up my formula. Students like this section because it really starts to boil down to the same thing, which is upper minus lower. That is until we start getting into some of the special cases. But nonetheless, that ends up creating our integral. Make sure that x plus 1 is first and x squared minus 5 is second. I like looking at this problem algebraically before I do the calculus. We always, well, at least it's often suggested to do algebra before calculus. What kind of algebra? Yeah, distribute the negative sign, combine like terms. It just makes for a little less to work with because, of course, negative x squared plus x plus 6 is equivalent to this integral. Now, I want to remind you that we have a tool on the calculator that actually allows us to evaluate an integral from A to B. It's called FNIT. It's in your math menu. Depending on the model calculator you have, it might look a little different when you activate the command. But remember, you type in 4 things. You type in the function. Notice that I typed in my simplified negative x squared plus x plus 6 function. And then you always put in an x. Some of you, it would be a dx that you put there. And then you put your A to B. I'm going to permit you to use FNIT for some problems. You'll see that unless I say that you have to show the antiderivative, like we did in the first problem, then you may use FNIT if you wish, as long as you understand that it is actually doing the integral for you, so you don't need to find the antiderivative. You actually can just record your answer to 2 or 3 decimal places. All right, so this problem, remember, we had to find the intersection points, and that helped us to get those limits of integration. Okay, so how about this one? Same thing, there's something new in this problem. I encourage you to pause the video, graph this on your calculator, and see if you can figure out what is different and maybe how to resolve this issue from negative 3 to 4. All right, so if you graph this on your own, I hope you saw a parabola that was opening down as well as a diagonal line with a negative slope. So where's the area? You'll find that that begins to be one of our main discussion points. Where is the area? Well, if your eyes seem to focus on this space in here, I would agree that that area is definitely between those lines. But what about negative 3? Did you investigate or notice that negative 3 is actually way out here? And what about 4? Again, did you investigate and see that that is over here? How does that come into play? Well, it comes into play by creating a boundary. And in this case, actually allowing us to extend our area to also include this space and to include this space. Because we want to go the whole way out to 4. So yes, this problem is requiring us to find 3 areas. And because we're finding 3 areas, we're going to have to subdivide. Now, you have to recognize that you're subdividing at these intersection points because at each of these intersection points, which happen to be at x equals negative 1 and x equals 3, at these intersection points, the upper and lower is actually switching. Okay, now this is a great opportunity to employ those strips that I was talking about, because it's pretty easy to see that the diagonal line is in the upper region in this first sort of interval, but now the parabola is the upper graph in this second interval, this middle interval, and well, it actually switches back to the diagonal line in this last interval. So we got a lot going on here. We have to recognize that negative 3 to 4 actually created a boundary, and we have to recognize that if we rub this off, that we have to subdivide since there was a switch that was going on. And so what does this end up looking like? Well, it ends up looking like 3 integrals. And so simply we go from negative 3 to 1. And in this case, it'll be the upper graph as negative 2x plus 2 minus the lower graph as the parabola as 5 minus x squared. Now, That's this first interval. That's this first section. But then I'm going to have to add to that my next section that goes from -1 to 3 of the reverse of the parabola being on the top and the straight line, the linear graph, being on the bottom. And one more time, from then 3 to 4 and back to where I originally was, the linear minus the parabola. Make sense? Okay. I'm running out of space, but we'll squeeze that in. And now there's no reason to worry about any negative areas, because since I subdivided, I'm allowing each area to come out positive. And that's also the idea behind this. So we're going to end up with 3 separate answers. Now, another good opportunity to use f and int. If you were going to do f and int, you'd have to plug in 3 times. Make sure you realize again that we get 3 separate answers for this problem. Again, I don't mind telling you, in decimal form we end up with 1066. We actually end up with another 1066. Interesting that both those areas are the same. And then this last little piece comes out to be 233. Of course, you're going to add all these together. Notice that they're already positive, and we end up with a total area of 2366. So the key to this problem, again, was that we had to subdivide because the upper and lower curves switched across this interval. All right, and we make our way to this next example, which is a little bit of a turning point in your learning of this lesson. That's because you can solve this problem using the skills that I've given you, but you're going to learn there's actually another way to solve it. Before we get to that, though, great problem again for you to try. I really, really encourage you to try to set this up. The graph's already been given, so what you're trying to do is think about how you're going to set up an integral or integrals. And I wish we could be in class, because you would discover that there's more than one way to do this. It's likely that you would do it differently than your neighbor. But why don't you try to get the answer, and then I'll meet you back here with some possible solutions. All right, now one of the popular methods that I see students use is often that they will subdivide this. If your eyes seem to notice that at x equals 2, that we can kind of split this into 2 sections. Yeah, because this first section, the one from 0 to 2, the upper graph is the square root, but the lower graph is the x-axis. So I can do the integral from 0 to 2 of actually just the square root function. The x-axis, of course, is 0, so we don't need to show that. And that'll give me my first area. Compared then to the second section, which is more from x equals 2 to x equals 4, where the upper graph, well, it still is the square root, but now the lower graph can be thought of as the x minus 2. And so if you subdivide this problem, now be careful that you're subtracting that quantity. If you subdivide this problem, you can end up with 2 separate answers. And it turns out that because we drew vertical strips, that this is a dx integration. We're going to be getting to that in a moment as a significant idea. But the first purple region there from 0 to 2 comes out to be about 1/88 and some change. I'm just putting a few more decimals just to be exact. And then this green region comes out to be, I believe, 49? And if I add these together, I can end up with a total answer. It actually comes out to be 3 1/3 using this subdividing method. Now, I've seen students also use a strategy where their eyes seem to notice this triangle over here, and to work that out, to actually want to do the integral the whole way from the beginning to the end, that is the whole way from 0 to 4. Now, just as a side note here, notice that these numbers that I'm writing down, they are x values, and so this would be the integral from 0 to 4 of the square root function as a dx integration. But then I would end up subtracting this triangular region. And of course, I'd have to find the area of that triangle. It can be found different ways. You could find it with a base and a height if you want. That doesn't really matter. But the point here is that you're still needing to set up and to sort of solve two parts to this. It turns out that if you do the integration the whole way from 0 to 4, that you get 533, and the area of that triangle ends up being 2, which takes us back to the same answer, 333. Once again, this problem was a dx integration because I did the problem with x values, but notice that I had to subdivide. Now, we always subdivide when there are different regions. However, I'm going to suggest that there's a new and improved way to find the area of this region, and that is using what's known as a dy integration. Now, some things have changed. Take notice to it. I actually have the equations written in terms of y. In other words, they are solved for x. So even though it's the same graph, the equation now is written as x equals y squared. And did you notice that the equation down here is written as x equals y plus 2? Now, that's pretty easy to see, but here's something that is now truly different, and that is that I actually want to draw my strips horizontally. I want to draw my strips horizontally because what I really want to see is which graph is to the right. And the graph that to the right is going to be known as the upper graph. And so if I do this with a dy integration, I'm going to be integrating the upper graph as the graph to the right, minus the lower graph, which is the graph to the left. Now, do you see how I have described these equations? I have described them in terms of y. So that means that the limits of integration are also going to be in terms of y. What I'm talking about is going from y to y. So what y value does this graph start at? Well, your eyes should be focusing on this y value right here, y equals 0. To this y value here, y equals 2. And this is going to be kind of a new way to look at these graphs, where now I'm going to be looking at the y values when I set up my limits of integration, since I'm doing a dy integration. Now, it's kind of interesting. I still can find the antiderivative. Yes, you can still add to the exponent. When you add to the exponent, you get 1/2 y squared. I can add to the 2. I can, of course, insert that y, and I can add to this exponent to get y cubed. And then you can evaluate this from 0 to 2. Now, this would be a good problem to actually put in your calculator to maybe just prove to yourself that it actually comes out to be the same answer. It does come out to be 333. The other thing that I would suggest that you do is to put the equation into your f and I and t, even though it uses y values. I can still type this in using the same formula. In other words, you type in the equation, comma, a variable, and then from 0 to 2. Just notice that I don't type in y, literally the variable y. I still have to type x, because that's the variable that the calculator uses as the independent variable. So a dy integration, it works out the same, but when and why would I use this? Why would I want to draw horizontal strips in a problem? Well, the answer is actually quite simple. It's so you don't have to subdivide. And the reason I didn't have to subdivide is because the right-hand graph was consistently always the linear graph, and the left-hand graph was consistently always the nonlinear graph. And so you'll get a little better at starting to recognize problems that involve a dy integration, again, because you don't have to subdivide them, since you're able to have a right-hand graph and a left-hand graph be consistent throughout the interval. Now, here's a couple summary slides that are definitely worth repeating and maybe copying down. We already told you that a dx is if you have vertical strips. A dy is if you have horizontal strips. Of course, the main thing here is going to be to start to be able to recognize this. So when would I want to use a dy integration? When would I want to have horizontal strips? Well, if the curve, if you see that there's a curve to the right, you'll want to call that the upper curve. And then your limits of integration will end up being the y values. Okay, now when you do this, or I say you typically want to do this when you see an x equals equation, in other words, an equation that's solved for x, or when you see that there are left and right hand graphs, and again, that are consistent throughout the domain. Go ahead and pause this if you need to, and the next couple problems I'm going to show you how to continue to work out dy integrations. All right, so let's look at a problem that's going to use a dy integration. I think you're going to see that there's a graph that is shown to the right. We're also going to want to get you to try to look for the y values. That's a little bit of a change in the way your brain looks at graphs. We're looking for the y values. And let's see how that works with x equals y squared and y plus 6 equals x. Now, as I've said it many times, these problems are visual. They require a graph. And once again, you want to be graphing this on your calculator. You want to see what it looks like on your calculator before I draw it. So you're typing these in your calculator, and there should be something that already comes to mind here, and that is that both these equations, although that they are solved for x, they need to be solved for y so I can see so I can get them into my calculator. Now, when you solve this one for y, you get plus or minus the square root of x. And when you solve this one for y, you get x minus 6. Okay, so this is kind of our next realization that sometimes you still have to solve the equation for y before you get it in your calculator. All right, so when you graph these, what you're actually graphing is two sides of a square root curve, which really ends up being a sideways parabola. Just so we understand, x equals y squared is actually a sideways parabola. And when we graph y equals x minus 6, well, we're getting a pretty familiar linear line with the slope of 1. Now, we're trying to find the area enclosed. You've seen a number of these now. You realize that that area is definitely between these two lines. What's more important here is maybe that we realize that the vertical strip that we're going to draw would actually be horizontal. The reason it would be horizontal is because every place along this interval, the upper graph, or in this case the right-hand graph, is always the same. The left-hand graph, well, it too is always the same. It's always the parabola. And of course, another reason that we're going to use a dy integration on this problem is because from the get-go, the equations were solved for x, which is a little bit of a giveaway that we want to be looking at the problem in this manner. So since it's a dy integration, we're going to want to find these points of intersection as y values. Again, it's a little different way for your brain to think. You actually, when you look at this on your calculator, you want to see y equals -2, and you want to see y equals 3. Now, I did just get those on my calculator, although there is a way to find those intersection points without your calculator. It would require a little bit of simple algebra, and that is actually just setting these equations equal to each other. If you do set them equal to each other, what you're really doing is solving them kind of like a little system. Since they're both equal to x, they can both be equal to each other, and I then can apply some pretty nice little polynomial math where we can factor this and solve it for its roots. You see, I hope that they come out to be the same. They come out to be y equals -2 and y equals +3. Do you have to do this on a calculator? No, you'll be able to have a calculator every time you do it. I just wanted to show you that it can be solved with algebra. Now, I'd like to say that the hard part is over. That is that we were setting up this problem, trying to understand that it's a dy integration. At this point, all I need to do is create my integral, which is the right-hand graph. Now, notice that I'm describing the right-hand graph in terms of y, minus the left-hand graph, which again, I'm writing it down in terms of y. To write it down in terms of y basically means to write down the version of the integral with the y variable. And since this is a dy integration, I'm going to make my limits of integration go from y equals -2 to y equals 3. So if I did the antiderivative, it would be a half y squared, it would be a 6y, and it would be minus a third y cubed from -2 to 3. Again, I can do the antiderivative with y variables. When you plug in 3 and plug in -2, you end up getting 20.833. You could also use F and I and T. I encourage you to do it one of the ways just to make sure that you too can get that answer. So again, as a summary, it was a dy integration, and that was because the equations were solved for x, but it was also because when I graphed these equations, we had a curve to the right and a curve to the left, which did not require us to subdivide. All right, so what kind of problem do we have here? Well, it sounds pretty familiar. We're trying to find the area enclosed, but if you notice, both these equations, or neither of these equations, are solved for x or solved for y. So there's nothing really that says, hey, this is going to be a dx integration or a dy integration until we start to dig into the problem, which is exactly what I want you to do. Again, if we were in class, I would tell you to try to set this up, see if you can graph it, and get an idea of what's needed. If you just wait to watch me do it, you might not know what it is that you know until you start the assignment. So push pause, graph this on your calculator, see if you can actually set the whole thing up, and I'll meet you back here with a solution. All right, so you do have to solve both these equations for y just so you can see what they look like. Subtracting x and taking the square root of both sides is definitely required, and make sure you get a plus or minus. Same thing here, subtracting 4x and taking the square root of both sides. Make sure you get a plus or minus. Sometimes people worry about this negative sign here as if you can't do the square root of -4x, but remember that x will just compensate so that we can end up with values that do exist. Now, when you graph these, you end up seeing two sideways parabolas. And it only takes a couple of these to start to notice that when the graphs are sideways, then drawing a horizontal strip is going to be the way to go, so that we don't have to subdivide. Now, sometimes students say, what do you mean so you don't have to subdivide? Well, if I tried to draw vertical strips, I can do that. Notice here that the upper curve is the green curve and the lower curve is the blue. But if I draw those vertical strips down here, now the upper curve is the blue curve. And so the upper and lower have switched. Not to mention, if I try to draw strips over here, the upper curve and the lower curve are the same curve. And so if I try to use a dx integration, that is, if I try to draw vertical strips, I'm going to have to subdivide because things change. But if I just draw and use horizontal strips, that is a dy integration, then the right-hand curve is always a green curve, and the left-hand curve is always the blue curve. Which leads us to our next realization, and that is that you then have to make these equations be in an x equals form so that you can put them into your dy integration. So subtracting y squared and subtracting y squared as well as dividing by 4 is necessary to get both these equations in terms of y. Now, maybe I should have done this back at the beginning, and that is to find our limits of integration, but both of these limits of integration are going to be y values. Make sure that your brain finds those intersection points, but more importantly, thinks of the y value so that when you set up your integral, you're going from y equals -2 to 2, and then we can set up our happy little subtraction, which is always the right-hand curve minus the left-hand curve, and that's all there is to it. The rest is you could put into F and I and T. That's what I would do here. I guess if you wanted to combine some like terms, you could, but really if you're going to put it in a calculator, it's probably just as easy. And the answer does come out nicely. It comes out to be 8. Make sure that you can get that. You don't want the first time you do this to be when it's graded. What's behind our little scratch off? What did we win on the lottery here? Well, in this particular problem, we had to solve for y to graph, but we had to solve for x to integrate. All right, now we have one more problem. I probably would have given this to you as an exit ticket, but I'm going to